So I have my sine wave again. If I hit trigger, trigger type edge, and you see I select edge, other choices will cause the signal to, again, fluctuate on the screen. It's important to pick the source because I'm triggering on this one signal. That's the one I'm displaying. And the slope, again, you can either keep rising, falling, or other choice. So I pick rising, and we'll leave it at that. So now you can see that I have my signal on my screen, and again I can adjust the amplitude, and I can adjust the time scale, and I can also move this up and down, and I do that by let's see, I do that by, this is moving it left and right, this is moving it up and down. So I'll put it at 0 volts. And my trigger level right here, you can see where it is. I'm just going to put that right at 0 also. And you can see that up there. Okay, so I have my sine wave here. Now I can do some measurement. So I'm just going to, rather than, there are cursors here that we can pick. 2 vertical cursors, 2 horizontal cursors that you can bracket portions of your curve and make different measurements. And that's always very useful. If the measurement menu that we have here doesn't give you the option that you want. But that's hard to believe because although we probably will use the cursors, but it gives you many options. So I'm going to push measurement, and you can see that, let's see, I want to pick peak to peak, so I'm going to pick, first of all, source 1, then I'm going to pick type peak to peak, and say that's okay. And we'll see here, so that's, no, we'll go peak to peak. Then we'll have to go back. So let's see. You have to scroll through all of these, I guess, till you get back to the top. The knobs will help us, probably. Oh. One of the knobs. Maybe not that knob. Type. Oh, here we go. There we go. This is the knob that will help us move up and down. We don't have to do that. So peak to peak, push to select. There we go. And now we see a voltage peak to peak, and we see that measurement here, and it says 2.07 volts. And now that's interesting. This says a peak to peak of 2.07 volts. Now my oscilloscope says an amplitude of 1 volt peak to peak. So why is that? Normally this waveform generator or function generator, goes by both names, has an output impedance of 50 ohms. You want that to be small so that you get the full value of your signal to your device under test. And so the reason they give you a choice, for example, of changing that output impedance is simply so that on your display device, in this case the oscilloscope, we get the same amplitude for the sine wave that we are sending to the oscilloscope. It's a point we'll discuss over the following weeks, but for now it really doesn't matter. It's just a display issue. So right now what I've done is I've pushed channel, I've pushed output load, and you can see if I set this to high Z, because my input impedance of my oscilloscope is 1 mega ohm, and I set this to high Z, I'll actually see on the oscilloscope a 1 volt peak to peak. If I pick output load and I set this to 50 ohms, you'll see what happens is that in order to match what I see on my oscilloscope, it's reduced my amplitude to 500 millivolts, which I can change by just picking amplitude, putting 1 volt peak to peak, and then we're back to where we started, where we see 2 volts peak to peak on my oscilloscope. One or the other, I think what we need to do is to just, let's just continue on, and we'll discuss this at some other point. So what I'm going to do is I'm going to go back to channel, output load, set to high Z, and then go back here and make this parameters, amplitude, 1 volt peak to peak, and now everything matches. So we're good. I'm going to just expand this in the vertical direction by just changing my scale. So now I see 200 millivolts per division, and I have 1 volt, 1 volt peak to peak. And now everything matches. Okay, so now what I'd like to do is I'd like to measure the frequency. So I'm going to go over here to measurement, which I already, let's see, I have pressed now. And I can measure type. And again, I can use my, rather than going up and down with the soft key, I can use this. And what I'd like to measure, I go down a little bit. I want to measure time frequency. And I can select by selecting. And I see my frequency is shown right here, and it's 100 hertz. And it's making actually a measurement of the period of my sine wave, which is the time it takes to complete one cycle. And you can see I have a correct frequency, which is what I set. Okay, so I have now a sine wave, and I can choose a square wave and do similar things. Okay, so let's clear our measurements. So we'll clear all. So now we have our screen again. So now I'm sending 1 volt peak to peak. And now what I'd like to do is I'd like to make some measurements on a circuit. So right now I have here my breadboard, which I'm just going to hold up in front of you in front of the oscilloscope screen. And I'm going to use just one of these little mini grabbers to point with, or rather one of these connecting wires to point with. This is our standard breadboard. And you need to understand how a breadboard is laid out. So first of all, you see that there are 1, 2, 3, 4 regions in which we can breadboard components. And you see each of these areas has a divide going up the middle that we see. Now, in one of these areas on one side of the divide, all of the little holes in one row are connected. So in other words, if I were to test continuity in any row, I would see that they're all connected. Now, on either side, and there is no connectivity across this divide. So on the other side of the divide, any holes in a row are connected. Now on either side of a region, I have these 2 columns with red and blue lines bordering them. Here, I have connectivity in any column and no connectivity in any row. So in other words, under plus, all of these holes are connected. Under minus, all of these holes are connected. And the same applies to the other side of a region. Under minus, all of the vertical holes are connected, all of the plus holes are connected. And then it simply repeats in these other regions, and I have no connection among these regions at all. So if you need to go from one region to another, you need to use jumper wires to do that. At the top, we have our terminals for our power. We have 4 of them, black, green, blue, red. Usually plus or minus 15 volts, plus 5 volts in ground. And we can make our connections here. And this is just for convenience, so we can make our power connections with the minimum use of wires. So again, everything is visible and understood. So what I've done here is I have 2 resistors. I've measured these already using our multimeter, which you should get out and make use of. I'm sure you've had some experience with that. If not, it's easy enough to learn. We'll do that in lab. And measure these 2 resistances. These are 1 kilo ohm resistors. Of course, they have a tolerance of about 5%, so plus or minus 5%, and they should be within tolerance. Over here, I have 2 mega ohm resistors, and again, 5% tolerance, and you can check that they comply. I've now set them up as a voltage divider. So I'm going to input my sine wave into this leg of the resistor. So I'm going to put my input into this row right here. And this leg of this other resistor will be my ground. And I'm going to measure where the 2 legs are connected. Now what we expect to see is the output, since these are 2 identical resistors, is the output should be 1/2 of my input. So let's see if that is in fact the case. So I'm going to make these connections. So I'm going to find the wires that first of all connect the ground to my, in each case, to my circuit, to my function generator, and to my oscilloscope. So you can see I have 2 ground wires here going to the bottom leg of that resistor. One input from my function generator has got to go to, and I'm fishing around here to find that, and I will in a minute. I have my red wire, and this is going to go to the input to my voltage divider. And so I'll put that up here. And lastly, from my oscilloscope, I'm going to measure the voltage where the two resistors are connected. So that's the output of my voltage divider, and I'll measure that. So that's how it's connected. So now if I put this down, then I come over here, and I'm measuring on channel 2. That's my input. So let me measure on channel 2. So I'll activate channel 2. And if I activate channel 2 and I then change to get to the same division, and let's see if I'm measuring correctly and have this connected. And it seems like I do. This is my input. And one of the mistakes, of course, is not wearing your glasses. So what's my excuse? I have my glasses on, and I don't have the input into the proper row. So this could have led to a real long debug session. But again, so if I go and I put this into that correct row, my signal will appear, and I actually see the green signal, which is channel 2, which is the output of my voltage divider. I see it's exactly half or thereabouts, and it's as I predicted. So again, one of the things that you have to learn in measurements in any discipline is you must know what to expect before you make the measurement. Because if I made this measurement and didn't know what to expect, I would look and I would say, is this right? And I couldn't answer that question. So you must do your modeling and analysis before, and then you make your measurement to validate what you predict. Predict and then measure. And this is a very important axiom that we sort of use in engineering. And so you can see I've done that. Okay, well, so if I then do one more measurement here before we quit, so let me just go to my breadboard here and let me then say, well, now what I'd like to do is I'd like to replace these two resistors with 2 mega ohm resistors. I'll just make the switch. So I'm going to take my 2 red probes out. I'll move my black probes out over here to my mega ohm resistors, and I've measured those to verify that they're mega ohm resistors. And I put those at ground. And again, I've lost which is which. So this is my actual input signal. I'll make sure I put that in the right row, and I do. And now this is the measurement from my oscilloscope. And this is going into channel 2, so I'm going to put it where these 2 resistors are connected, and that's true, that's right there. And I should see that I now measure half of the 1 volt peak to peak. And again, I must be in the wrong row. And I am, again, indeed in the wrong row. So, as you can see, I don't see well with my glasses. So I put this in the right row. And now I see that, indeed, what I'm measuring is less than half. What am I measuring peak to peak? So what we see here is that what we might expect is that the peak to peak should be around 0.5 millivolts, and it's not. It's 0.380 millivolts. So I leave you with this question. When we used a voltage divider of 1 kilo ohm resistors, we got what we expect and predict is an output of half of that. When we used a voltage divider with 1 mega ohm resistors, we got an output that was not a half, but a third of our input. Is that surprising? I ask you that question. And as a hint, let me ask you tell you that the input impedance of the oscilloscope is 1 mega ohm. And 1 kilo ohm is simply 1/1000th of a mega ohm. But 1 mega ohm resistor is equal to the 1 mega ohm input impedance of the oscilloscope. That must have something to do with it. So that concludes this presentation. I know it's rough, I know it's crude, but this gets you started. And we learn by exploring as you do. So have fun exploring. Measurement and control and using these instruments will certainly enhance your professional careers. So take this seriously and become expert with these instruments, and you'll never regret it. Thanks.